Hey there, let's prove this statement. So this statement should make sense first of all. Let's say we have our real number line, and you have x and y. Multiplying x by some positive integer will eventually get us past y. Now if y started being less than x, then by setting n equals to 1, the statement would be true. Let's get into the proof of it now. So, for the proof, let's set s equal to the set of z times x, where z is a positive integer. Now let's assume this original statement's false. So what would that mean? Well, it'd mean for any positive integer n, we'd have y being greater or equal to n times x. Now that would make y be an upper bound to the set s. And clearly s is not non-empty as well, since, for example, z equals 1 produces an element of s. And now, since s is a subset of the real numbers, and the real numbers have the least upper bound property, this implies that we get that the supremum of s is in R, and it's the least upper bound of s. So the supremum of s is in R, and it's the least upper bound of s, right? Okay. So, what does this mean? Well, nothing yet, so let's do something with that. Well, the supremum of s minus x has to be less than the supremum of s. Now the reason that is because x is positive. Now if it's less than the supremum, and we know that the supremum is the least upper bound, anything smaller than it must not be an upper bound, meaning that there is a positive integer where the supremum of s minus x is less than m times x. And that's since it's not an upper bound, meaning there is an element in here greater than it. Okay. Now we can continue with this. If we add x to both sides, this would be saying that m times x plus x, that would be a true statement, and that's equal to m plus 1 times x. Now, that's still a positive integer, and that's still x, and so therefore that's an element of s. But we found an element of s which is greater than the supremum of s. Now this is a contradiction, since the supremum of s is an upper bound, meaning it should be greater than all elements of s, but we found one larger than the supremum itself. Therefore we have our contradiction, and so the original statement must be true. So now that we've done the proof on paper, let's see what it looks like in Lean. So as always, we'll start by making a theorem. And we're going to call this the Archimedean property, since that's what we'll be proving. And we're going to take x and y being real numbers, x being a positive one. And from there, we were going to prove that there was a natural number being a positive one, and y being less than n times x. Now to begin the proof, we'll make a begin and end block. And if you recall, we defined a variable s, which was a set of real numbers, and we defined it as the collection n times x, which was a real number, of course, and n being a natural number, but not only natural, but also being positive. And from here, we decided we'd do a proof by contradiction. So in Lean, all you got to do is do by contra, and we have the negation as our hypothesis, and we'd like to get to a contradiction. So when we stated the negation, we said for every natural number which is positive, y should be greater or equal to n times x, and to make it look like that, we're going to push the negation through at h, and so then we'll have that, which looks more like what we were talking about. Now we'd want to use the least upper bound property of the real numbers, and what that says is for any subset of for the real numbers, which is non-empty and bounded above, then its supremum exists in R, and the least upper bound of that set is the supremum of that set. So the way we get to that is we'd first want to prove that it's non-empty. So we have that our hypothesis being that S is non-empty, and it's of the type S non-empty. And we'd want a proof of that, of course, which we'll delay for later. And then we need the fact that S was bounded above. And then from there, we'd have a proof of that as well. And given that we have those two proofs, we can now use that theorem, which is that the supremum is the least upper bound. And we can get to that by is lub sup, using S, using the fact that it's non-empty, and using the fact that it's bounded above. So now, what did we do? Well, if you remember, we then did some subtraction, and what we did was we had that the supremum minus x was less than itself. So what does that look like? Well, what we were trying to show was the supremum of s minus x was less than the supremum itself. And we'll need a proof for that, of course. And once we have that proof, then what did we do? Well, since it's less than the supremum, that means that this number, supremum of s minus x, is not an upper bound. And if something is not an upper bound, it means there exists an element from that set which is greater than it. And in Lean, in Lean there is a theorem in MathLib which helps us get to that. So let's make our variable name be there exists an element greater than, and we're going to use exists lt of lt c sup, and we're going to use the fact that s is non-empty, and also that the supremum minus x is less than, and little typo. So now we would have that there exists an a, which is a real number, a being an element of s, and it being greater than sup s minus x, which is exactly what it means not to be an upper bound. So from here, we want to get that element which exists, and let's get that hypothesis out of there, and also extract the arithmetic inequality there. So we can do that all at once in Lean by using our cases, and we're going to use it on that which we just defined. And then we're going to use it with breaking it apart using a, h, the hypothesis that a is in S, and then that the supremum minus a is less than. And once we've done that, we'll see what we get out of it. So as you can see, we've broken it up into these three nice pieces, which can be used easy. So let's now use them. Now, one thing to note is that a is an element of S, and being an element of S means something. So what we can do is extract out what that means, which is that a equals n times x for some n, and then rewrite this inequality. Now in Lean, we can do that all in one step using obtain, which uses our cases and have, and then we can do n, hn, and then RFL, which will rewrite the inequality that we were just talking about. And then we're going to break apart a and s, since that's what would give us that information. So as you can see, it's just rewritten it here, and that's RFL, which did that for us. So now, if that's the case, then we should also be able to add 1 to n, multiply it by x, and that inequality will still hold. In other words, we should have that it's less than the successor of n multiplied by x. And then what we're trying to show is that the supremum of s is also less than n plus 1 times x, and we'll have a proof of that. And then what we'd want to do is show that n plus 1 times x is an element of S, and from there we'll have a contradiction. So let's first have it, which is the supremum, or sorry, the successor of n multiplied by x is a member of S. So what would that look like? It'd be n plus 1 times x is an element of S. Now there's an issue. Since x has type R, but n plus 1 is of n, you need to coerce n plus 1 to be also a real number. And the way we do that is by adding a colon and R. So now that should be fine. And we would prove that. Now with this being the case, if you remember from our original proof, we were able to then show that the supremum was not a member of the upper bounds. And that would look like the supremum not being a member of upper bounds of S. And we'd get a proof of that. And now, given all these proofs, we'd be able to finish the proof because we know that we have the fact that the supremum is not a member of the upper bounds, but also it's the least upper bound, and so therefore it is a upper bound, and that information can be extracted from the fact that it is the least upper bound, and then from the second part of that, we are done. We've reached our contradiction, and the proof is complete. Okay, so you made it through the proof. Well done. Now, there are some sorries left. I want those to be exercises for you to fill out. And on the other hand, if you just like to learn more about MathLib and not really do that as an exercise, then since I'm a mathematician who's also trying to make a living, I would recommend going on to Patreon and making a subscription there. And by doing that, you'll gain access to all of the content I've ever created on Patreon, including an exclusive video talking about how to fill in these sorries and my workflow about what tactics I'm using and how I came up with the theorem names for the ideas I have in my head. And yeah, I hope you go check that out. I find as a beginner, knowing this information would definitely boost my skill using Lean. But otherwise, I hope you're able to finish the sorries and have a good day.